Hey, what's up, guys? This is Chung here again. So today I'd like to talk about today's daily challenge, which is number 456, 132 pattern. I think this is a great problem. So given like an array of integers, like numbers, so it asks you to find a pattern. So a pattern is 132. So which means that you need to find like three numbers, right? So which the index is I is smaller than j is smaller than k, but is the number I is smaller than both j and k, but the number k is greater than the number j. So that's how you define this 1 3k. Okay, so from left, middle, and right, but the sequence of the middle and right is the value is the reverse. Okay, and they ask you to find like to try like a better solution. Okay, we'll talk about this time complexity later on. But so some examples here, right? So the first one is like this. So there's like obviously there's no 1 3 2 pattern here. So here we have a pattern which is like this, 1 4 2. So 1, 2, and 4. Okay, and here also we have a few candidates here, right? So we just return true if we find any of the candidates. So for this problem, how can we approach this problem, right? I mean, as you guys can see, we have several conditions we need to match here. So the first one is let's say we have a number. So for one, we have number one, right? Okay, so we have number one, we have a number three, and we have a number two. Okay, so representing each of the numbers here. So what are the three conditions here? So the number three, so the two and the three needs to be greater than one, right? So that's the first one. And the second one is the what? Is the three is greater than two. Okay, so that basically that's the two conditions we need to satisfy here. And every time when you guys like maybe next time when you guys see like a similar problem that you need to satisfy like different like more than one conditions. So first thing first is that we have to do some pre-calculations to help us to satisfy one condition first. So that at one location, at each of the location here, we can simply utilize that one condition, right, to help us to. Otherwise it will it will be most likely O(n) square solutions complexity here because we need to check both the left side and right side. And for in this case, it's better to use number three as a checkpoint. Okay, because it's easier to verify. Basically, we just need to check um, what's the minimum value on the left side, and if there's any numbers on the right side, which is smaller than me but greater than the minimum value on my left, right? So to get the minimum value at the current location, I think it's pretty straightforward. We can do a pre-process. Okay, and every time when we do so basically we loop through the arrays from start to the end, and then we try to calculate the the current minimum value we have seen so far, and we'll populate that so that later on when we try to use this number here, when we add this number three here, we know okay what are the smallest number on my left. So that's one thing. That's a technique. If you ever want to reduce your time complexity, always try to think about pre-processing so that you can get one condition with O1 time. Otherwise, you have to do a loop that will be O(n), right? And the second one is the the how can you find another side, right? If there's any numbers on my right side which satisfy two conditions. The first one is that it's smaller than me, and second one is greater than the letter on my left side, right? So for that, it's I think the best solution, the best option is to use a monotonic queue here. So in this case, it's going to be a decreasing queue. And okay, so I will give you some examples here. Let's say we have like, and also to be able to find the numbers on my right, smaller, which is smaller than me, we need to traverse from the end from the end to the start. So we can find the numbers on we can know what are the numbers on my right side so far. We have seen so far, right? So I'll give you some examples. Let's say we have like 2, 5, 8. I'm writing this number from backwards here. So here we have a 6, okay, and let's say we have a 7, 8, 9, and 7. So let's assume this is the number. And assuming we already have like pre-processed the minimum value here. And like I said, since we're going to traverse this number from backwards to from the last to the first one. Okay, and then we're gonna have like a monotonic queue here, right? So the monotonic queue is we're maintaining like a decreasing queue here. So which means that at 8 here, right? So 8 we have 8. We have 8 and then we have 5. So this is a queue, right? And by the way, I'm drawing this queue following this sequence here. So this is a 0. This is the index 0, this is index 1. Okay, and this is index 2 and so on and so forth. And now we have a 2 here. So to maintain like a monotonic queue here, right? So we only pop this item whenever whenever the current item is bigger than top one. Otherwise, we just keep pending, right? So that's why we have 8, 5, and 2 here. So if that happens, if we keep expanding appending, nothing happens because we know there's no. Basically, we're looking for with the current number 3 here. Every time we're at the like index here, we're assuming that number is number 3. Okay, that's number 3, and then our job is to find you know, since we have pre-processed the minimum numbers, so it's kind of like we already have the number 1 here, and now we have number 3, right? So the only job left is we just need to find a valid number 2 that can satisfy these two conditions, right? So that's why, if we keep like increasing, like if the number just keep decreasing, then we know we couldn't find a number 3 which is bigger than the 2 here. So now we're at 6 here, right? So we're at 6. Now the 6 it's bigger than 2. Then we know, okay, cool, finally, right? Finally, we find an answer. We find the answer that find a candidate that can satisfy this condition, right? This condition 2 here. And then every time when we have like a candidate, right, we'll check, okay, so if this 2 is greater than the minimum value on my left. Okay, so what's the minimum value on the left? So here we have a star here because it doesn't really it doesn't make sense, right? Because, oh, by the way, so when we're doing the reverse traverse here, we'll stop at here. That's the ending point, right? It kind of makes sense, right? Because we're picking this number 3 here, and when we are moving at the first element, so there's no such number 1 on the left. So that's why the first candidate we don't need to consider the first one. So we'll only stop here. Okay, back to the minimum queue here. Okay, so with the minimum. So the minimum queue, the minimum arrays records the current minimum value on my left. So here it doesn't make sense, right? So here we have 7. How about here? Also 7, right? Here's also 7. Yeah, here 7, right? And then here we have 6, right? And then we have 2 and 2, right? So that's the minimum value. So at this moment here we're at 6 here, right? And then we pop this 2 out. And then every time we pop like an item, right? We know, okay, we find like a candidates that satisfy the second condition. Now I just need to make sure if it can satisfy the first one. Okay, so and since the 3 is greater than 2 here, and as long as I can check, make sure if 2 is greater than the minimum value, then we find the answer, right? And then, but 2 is smaller, it's not greater than 7. Okay, 2 is not greater than 7, so we just pop it out, right? And then we do the next one is 5. 5 is also not greater than 7, so we pop it out. Now we have a 6 in this queue here, and then we will try 7 here. Okay, so why we can pop this 2 and 5 out, right? Remember, we're assuming, okay, so in this monotonic queue here, remember, so this is like the candidates, number 2, num2 candidates, okay? We're always storing the number 2 candidates in this queue here. And while we're popping this 2 here, if the 2 is smaller than the minimum values on the left of 6 here, it means that all the numbers on the left of 6 is greater than 2, right? So which means that 2 is not a candidate of number 2 anymore, because all the numbers on the left side is greater than him, right? So that there's no number 1 basically, right? So we have to shift this number. We have to find another number number 3 or number 2. Same thing for number 5, right? So basically for both 2 and 5, for both 2 and 5, and all the numbers on the left of 6 is greater than them, right? So which means that there's no so this 2 and 5 will never be able to help us form a 1, 3, 2 patterns, so that we can safely remove them from the monotonic queue. But 8 is not, we are not sure, right? So why is that? Because we know that anything on the left side is greater than is greater than the 2 and the 5, but 6 we're not sure, because this 8 8 is greater than 6, right? Since it's greater than 6, and then we're not sure if anything on the left side is greater than 8 or not. That's why we need to keep this 8 here, and that's why we're using like this decreasing queue to help us to track all the validate number 2 candidates in this queue for each of the numbers here. Okay, and now the 7, right? So when 7 comes in, right? So 7 comes in, same thing happens, right? Same thing, we check, okay, 7 is greater than 6, right? And then we just pop the 6 out. And again, we compare, okay, so if 6 is greater than 7, nope, right? So 6 is not greater than 7. So it means that all the numbers on the left of 7 is greater than 6. So which means 6 is not a valid candidate anymore. So we can simply remove that. Now we have 7 in here, right? Now same thing for 8. Okay. We have 8 here, and 8 is greater than 7, but it's okay. So 8 is greater than 7, so we pop these things up. Now we have 8 here, and we also have 8 here. And I mean we can also pop this 8 out, right? Because we don't need like a same value here. Yeah. So and now we have a let me see here. Yeah. Okay, so we have 8 here, right? So 8 is greater than 7, so we removed 7. We put 8 here. Oh, by the way, we cannot pop 8 here. Again, why is that? Because the rules for the popping up is strictly increasing. Sorry, it's strictly greater, so we can satisfy the second condition is here. So if we're popping this 8 here, basically we're assuming this is equal, right? That's why it's not like a strict increasing, a strict greater greater than the number here. That's why we cannot pop this 8 here. So we have 8 here, right? And finally we are at 9. We are at 9 here. So when we're at 9 here, we see okay, 9 is greater than 8, right? So now 8 is gone. And so is 8 greater than the 7, than the minimum value on the left? Yes, it is. Finally, right? Finally, we have another candidate. When we pop this 8 out, right? We have seen this 8. Oh, finally, 8 is greater than 7. Now we finally find our 132 pattern. Cool. So that's it. So let me do the coding here. So like I said, I need a minimum list here, right? And then the way I'm populating the minimum list is like first I'm going to have like current minimum, right? So to start with, I'm having a 0, right? And then we have for num dot in nums. Okay, so every time I do a append first, so which means that I append the values for the previously numbers. Okay, that's how I calculate the minimum numbers on the left, right? So that's the minimum. So for the first one, actually, it doesn't really matter because we will not be using the minimum value for the first element. So I'll just use the number itself as that, you know. So and then after that, I update the minimum, right? Okay. So that's that. Okay. So now the decreasing queue, right? So like I said, we need to maintain like a monotonic queue for all the number 2 candidates. So now like I said, I need to traverse from the end to the beginning, and then I stop at index 1, right? Mm, and the current number is number 3, right? So that's the number 3. And while I'm popping up the number 2 candidates, right? So here is like number 2 candidates, okay? Candidates. I do decreasing queue, and the number 3 is greater than the decreasing queue dot minus 1. So now I have a num2 candidates because this is and okay, this is strictly greater. That's why we can satisfy the second condition. Okay, and now I just need to know to check if the number 2. Sorry, I need to do a pop first. Okay, yeah, pop, and if the number 2 is greater, right, then the minimum values on this number 3 is left. If that's the case, we simply return true, right? Of course, though, the last thing is to maintain this monotonic queue here. Otherwise, it's safe to pop it out because all the numbers on the left of number 3 is greater than number 2. So this is not a valid candidate anymore. We can safely pop it out. Okay, and then in the end, return false, right? Cool. Run. Oh, sorry. Underscore, run the code. Okay, so accept it, submit. What? Mm, let me see. Oh, probably here. Yes, number 3 here. Yeah. Update number 3, submit. Cool. All right, so accept it. And as you guys can see, it's very fast because this is it's a O nth time complexity. So here we have an n here, right? So the first loop is O of n. And here, you know, it seems like we have like a nested for loop here, but you know, so you so the nature of the monotonic queue is that, each number will only be pushed and popped to this queue one time. That's why. So here within this for loop here, so here actually is O of O1, you know. That's why the total time complexity for this solution is O of n, right? Total time complexity, yeah. And the space complexity, of course, is O of n. All right. Cool, guys. I think that's it for this problem. Yeah. Thank you so much for watching this video, guys. Stay tuned. I'll be seeing you guys soon. Bye bye.